Good morning, my dear students. Welcome to the session on moment distribution method. So, last session we have talked about this carryover moment. Came to know that the moment developed at the fixed end is called as carryover moment, and carryover factor is nothing but the carryover moment by applied moment will give you carryover factor. Right. In this session, let us see what is meant by stiffness of a member, right? Okay, so let us see this moment required. So generally, we say stiffness in the sense. So K immediately when I ask you what is meant by stiffness, if you say it is simply P by delta. Okay, so load divided by displacement at the corresponding point where the load is applied and in the direction of the load. This is what actually the complete meaning of the stiffness. Okay, so whereas we just say it no what is the stiffness means, just load by no deformation. Okay, ratio of load to the deformation. But what does it mean, right? If you apply force at a particular point, and if that point deflects in the same direction where the force is applied, that deflection you shall calculate. Okay, so simply, just for example, I'll just show you an example. So we apply point load here. So when you look at it in actual sense, that this cantilever will bend like this, and it has to be little less in length, right? When it bends, it has to come towards fixed support. So which means the point which is here is not this value. You shall calculate this value occurred in the direction of the load and not this direction. Okay, but anyhow, with the assumption that this quantity is negligible, and we are taking that itself as vertical. That is our assumption. So PL cube by 3EI is the deflection value delta. That is actually not vertical. Okay, so this is how we define stiffness. When you apply load, the deformation is deflection. That's why you are taking the corresponding quantity. So what this will cause, the load will cause member to deform, so it will deflect. Whereas what moment will cause to the member, it will try to rotate, right? So that's why stiffness of a member when moment is applied is calculated moment by theta. Okay, so now we want this to be defined, not this general form. Okay, got it? So stiffness is defined when you apply moment, it is the ratio of moment to the corresponding rotation of that point where moment is applied. Okay, let us see that. So moment required to rotate a point where moment is applied in a member by unit angle is known as stiffness. So what does that definition mean? So if m is equal to, if I rearrange that equation, k into theta. So if theta is equal to 1, m is equal to k, for theta is equal to 1. Okay, so moment required to rotate a point where moment is applied in a member by unit angle is known as stiffness. So stiffness is equal to moment required when theta is equal to 1. That's it. So that's how we define the stiffness of a member. Okay, so this is a point A, where you are applying the moment, and that point is rotated by an angle of theta A. So K is nothing but m by theta A for that member at that point. Okay, got it? So this is the formula for finding stiffness in terms of mathematical expression. Whereas if you want to define it, so you have to define like this: moment required, moment required to rotate a point A, where moment is applied in a member by unit angle. If theta is equal to 1, that moment is equal to k. Stiffness, okay, is known as stiffness. So moment required to rotate a point by a unit angle is known as stiffness in simple words. Okay, so you have to understand that the rotation of a point and moment applied are at the same location. You have to understand that. Okay, so moment required to rotate a point by a unit angle is known as stiffness. Moment required to rotate a point by a unit angle is known as stiffness. Okay, and you have to understand that the moment applied and theta are at the same location. Okay, so simple words, stiffness is equal to moment required to rotate a point by unit angle is known as stiffness. Okay, right, let's go to the next quantity that is required for moment distribution method. So distribution factor. So what is distribution factor? So imagine that there are four members meeting at a point O, okay, and you have applied some moment at the joint, okay, joint. On the joint, you are applying moment M to rotate that joint, okay. The joint is rotated, okay, not individual members. So what is meant by distribution factor? Ratio of moment shared by a member to the moment applied at the joint is known as distribution factor. So for example, if you applied some 100 kilonewton meter, say member OA, if it is taking say 10 kilonewton meter moment, so nothing but this is 10 and divided by 100. So distribution factor is 0.1. Okay, got it? 10 by 100. So nothing but if you apply a moment at a joint where number of members are meeting at that joint, the distribution factor is defined as a ratio of moment shared by a member to the applied moment. Okay, so this is how we define distribution factor. Okay, so but the total distribution factor total should be 1, right? 1. If you add all the quantities shared by each member, for example, all are of similar in nature, so I'll just take 25 each, let us say 25 each. 25, 25, 25. They are sharing the moment 100 applied to 4 equal parts, let us say. Okay, so 25 by 100, 0.25. Okay, so let us say this is 25. So 0.25 for each member. So likewise, if you add all those values, okay, so 4 times 0.25 is equal to 1. Means what? The distribution factor, a total distribution factor at a joint should be 1. Okay, so this is about distribution factor. Okay, so if a moment is applied at a joint where number of members are meeting, the distribution factor is defined as the ratio of moment shared by a member to the moment applied at the joint. Okay, so just to recall what is studied in this session, so we have talked about stiffness, and the general sense of stiffness is different from the one which we are defining now. In general, stiffness means load by deformation delta, but here it is related to moment. So m by theta is formula for stiffness, and we have defined it. Okay. Similar distribution factor we have defined, and the total value of distribution factor at a joint should be 1. Okay, right. So next session we will come back and talk about the formulas for carryover factor and stiffness and distribution factor, right? We will develop formulas for these 3 quantities: carryover factor, stiffness, and distribution factor. We'll develop the formulas. Okay, right. Thank you.